right hand, like, doing
All right.
everything, like, that we do in academic innovation. So she'll be the one starting, like, our live.
So are you ready? I'm going to make the Q, classic Q. Ready.
All right.
We are live. Go ahead, yeah.
Mm-hmm.
Hi, everyone. Welcome to join our academic innovation support live stream. Today, we're back to our quantum topic, and we will have a special conversation with Classiq Q. Uh, so joining us is Rolf, the quantum application engineer from Classiq Q, and also Eric, the head of technical marketing. Of course, one of our regular guests is the lead of Wolfram Quantum team, Mats. So I will let them start the conversation.
Excellent. Thank you, Lee. So very happy to have Ron and Eric, two of our good friends and partners on Quantum. Let us just start, like, with this big confusion about, like, the name of the companies, like, having, Q, because all people, when they read that, they will say, shall I pronounce it as Classiq or shall I go Classiq Q? Like, how should I pronounce the name of the company? Let's just start with that.
Yeah, we tend to go with Classiq ourselves.
Mm-hmm.
But a lot of people also call it Classiq. It's a
Mm-hmm.
little fancier, but we tend to call ourselves Classiq.
Nice, nice. So let's see, like, our plan for today is to have a conversation, regarding, like, the great functionalities that you guys have been developing on Quantum, spatially, like, considering, like, real world applications, and of course, like, integration with Wolfram Mathematica that opens up the possibility, like, spatially in academia for students, users to explore more, like, great functionalities that you guys have. So, Eric, Ron, whoever wants to take the lead on that, let's just start that conversation.
Yeah, absolutely. So, I mean, again, thanks for having us on here. I've been loving working with you and the rest of the team, and let's show a little bit of a slideshow I got here to kind of frame things out. And yeah, if anybody has questions during the live stream, feel free to ask anytime along the way. I talk about quantum all day, every day, and it's what I love to do, so feel free. All right. So yeah, well, we're Classiq, we're quantum computing software. And as Mod said, we're working on integrating together with all the great things happening with Wolfram. So what Classiq is we're an end-to-end software development platform. We have a programming framework that has high-level modeling. We're hardware agnostic, which means any of the code you build will work on any of the hardware you want to run on. And it's for developers with both, high quantum knowledge and for those who aren't coming from a quantum background as well. Um, and for those who aren't as familiar with quantum, right? Quantum is just a new way of doing computing. Instead of bits, we're using something called qubits, probabilistic bits at the end of the day. And there's some pretty
Hmm.
cool things you can do in maths with it. But the reason people are interested in the first place, from a big picture point of view, it's going to allow certain things to be done, essentially less computationally intensive, certain calculations. So the same way that the advent of the GPU made certain types of calculations less computationally intensive to perform, it enabled a lot of cool things. We were able to do things faster. Same thing's going to happen with quantum computing and quantum development. And there's lots of different algorithms that are out there in the universe of quantum, and that means there's also lots of different applications depending on what you're looking for using it. So there's a whole myriad, whole sleuths of problems, and we'll get into some of them later. But it's a wide-reaching technology that's going to affect a lot of different industries. And right now, just so kind of framing things out, the state of quantum computing, a lot of people call this the NISQ era. It's a word you're going to hear if you do any Googling of quantum, noisy intermediate quantum. The hardware is a little bit noisy right now. But there's lots of different ways to make hardware, lots of different kind of hardware modalities, the physics of making these kinds of quantum particles. Lots of different manufacturers and developers are building out different machines, but they're all increasing in size, essentially, right? That's kind of the message. There's lots of different ways to do it. We're in this kind of noisy era because the machines are being built out and developed, but they're all scaling quite lovely. And frankly, I haven't been part of a bleeding edge industry that's actually kept to their roadmaps. So I'm actually quite amazed that we actually have kept to each of these hardware roadmaps for companies. And kind of the modality for programming these systems is at this kind of assembly level language. If you're looking at this code, what quantum coding looks like, each of these lines is a qubit, or the particle that you'd be kind of doing your computation on, and each of these blocks on the screen are essentially the calculation of the operation you're telling that specific qubit to do. It'd be essentially the equivalent of Boolean logic for your bits. And kind of this is what we hit with what we call the quantum software challenge, is that it's kind of like punch card programming, this kind of modality of programming. And large in part, this is not going to scale. I don't like to use the word impossible to design very large quantum circuits, but I'll say grossly impractical. I think anybody, if they spend a long enough time, someone will prove you wrong and say, oh, I can actually do a 125 qubit quantum circuit by hand. I'm sure you could. I don't know how long that would take you. So grossly impractical is the verbiage I tend to go with. And I don't think anybody would argue against that. Doing it by hand, that would just take you a hot minute to build any kind of large quantum program. And the same way with classical programming, right? If you're trying to build an application that's worth its salt, it's not going to be on 5 bits, right? It's going to be thousands of bits, and you can't be doing that in Boolean logic. It's just grossly impractical. Yeah, and kind of programming for these systems needs kind of a holistic approach at the end of the day, right? You have your problem space, you have your solutions you can develop, but you need context around that problem. What is the hardware you're going to run on? And there's so much kind of minutia when it comes to programming quantum stuff right now that you have to know what hardware you're going to run on, what's the connectivity for that hardware, what are the native operations for that hardware, how do you balance the efficiency of what you're trying to code in versus how that affects the hardware and the algorithm you're putting it into. And largely what what the Classiq does for quantum is it abstracts out a lot of that context and what you'd have to know as a programmer to build efficient quantum circuits, so that you have to be just an expert on the problem you're trying to solve. And you still have to use quantum to solve it, but you don't have to be kind of that low-level machine, quantum expert to program these systems, which is why Classiq helps out for both quantum and non-quantum experts. It's more on the programming end. You program efficient quantum code that uses the hardware instead of having to know all the minutia of the hardware itself. So it abstracts out all those kind of hardware constraints. And it looks through a huge phase space of different possibilities for you to get that efficient quantum code that will run on whichever of the hardwares you're deciding to choose and go on. And hopefully what we're trying to do with you and your team's mods is kind of help people go through the whole quantum computing roadmap, right? A lot of people start off with kind of the exploration phase and they built some small quantum circuits and they stop. They don't kind of go on to the next stages, right? And that's what we're really hoping to do with Wolfram and everything there and all the great applications you have. I've done this both in the lab and in industry when I worked for Kodak Alaris, actually. I was in their innovation department for a while, and we used Wolfram, and you start off with a small program, a small project, then you got to pilot it somewhere. You got to build some infrastructure. You take that kind of rough work you did and you scale it up. And that's where a lot of clients and a lot of people
Hmm.
working in quantum in any, scale phase, it's that scale up that they have a lot of trouble with. And how do they investigate this in a way that is actually practical?
Hmm.
Um, yeah, and I can go into some more things here in general, but there's a lot of reasons people are investigating it. There's a lot of, McKinsey put out a report saying there's a lot of money coming into quantum in the near term for a few kind of key industries. There's some key algorithms that are really important, and depending on how the conversation goes with the audience, we can geek out about some of these variational quantum algorithms and things like this, kind of the near-term quantum technologies. But I'll kick it off back to Ron, who can talk more about what we're doing on the integration and how we're working together.
Excellent, excellent. So basically, like, one thing that, like, Ron, you can, as I'm sharing a few thoughts with our users. You can go ahead and share your screen. One thing, regarding, Mathematica, that many of our users, like, they know less compared to many other functionalities. And Ron, like, he's gonna showcase, like, a few of them is many of, like, these platforms to do fancy quantum computation, such as what we have in Classiq. They are built in different, ecosystem. Like, they are building, Python environments, and, like, some of our users, they would say, gosh, like, this is Python, and, like, I'm a Mathematica users. Like, what about the integration? And this is the part that I would like to remind the users that, like, the encapsulation of, other programming languages in Mathematica notebook, it can be done so easy. And if you do that, like, you're going to benefit from the power of both platforms. Like, you can get all the functionalities that you have in Classiq, plus any other functionalities that you can use, like, in Wolfram Mathematica. So let's look at a few of them, Ron.
Yeah, great. Thank you so much, Mads, and thank you, Eric, for the great Classiq introduction. So just as a small agenda, I will present two examples. The first one will focus on what can we do with arithmetic in Classiq based on like a use case of Brownian motion, which I will show. And the second one will be more in the chemistry field, finding optimal solution to molecules in a classical way versus a quantum way, and comparing them. And like, I'm open to discussion, so feel free to stop me however you like. Okay, so so modeling Brownian motion. So let's start with what is Brownian motion anyway. For who doesn't know it, is that particles in liquid or anything are moving randomly up and down because some other particles move them. And like the GIF showing it the best way, that there is some random behavior of the movement of this particle. And there is like a lot of analysis that is done on in the physics departments everywhere to model this Brownian motion. And this is in physics. Taking it to the financial world, if you think about a market where people are buying and selling some assets, so it's behave very much like the particles that is pushing up and down. Any exponent of this up and downs represent the actual price of some assets, so which has also some random behavior. And there are mathematical models behind such behavior, which are Brownian motion actually. So let's see how can quantum computer help us to analyze such behaviors in financial markets or in physics of Brownian motions. So Eric gave a great introduction and told you that the difference between a classical bit, which can be 0 or 1, to a quantum bit, which can be 0 and 1 at the same time. So the idea is that we brought, one of the ideas we brought with Classiq is that if we have quantum bit, why not having a quantum number? So if I can be 0 and 1 at the same time, so a quantum number with 4 qubits can be 16 possible values at the same time. So by using just n qubits, I can hold 2 to the power of n values at the same time. It's coming to imply about the power that quantum computers bring. So if it takes thousands of qubits, so you have 1 and 300 zeros later of numbers that you can hold in a computer at the time. So we have a quantum number, and now we would like to see how the idea of compilers that is able to tolerate quantum numbers and to make operation and operations that feels to us basics in the classical world, like addition and multiplication, is done in the quantum world. So now let's be more practical, connected to some use case. So JP Morgan and Chase Bank, the biggest bank in the world maybe, they published an article on February that is telling how to model option pricing in financial market using Brownian motion. The article was published in February. It was totally theoretical, and it says that the Brownian motion is some random variable that is described with a lot of summation and multiplication and a polynomial which is defined in a recursive way, the Chebyshev polynomial, if you know, and that something that writing in a classical computer is trivial, because in one line you could do multiplication and addition and everything is okay, because we're regular to the fact that the classical computers are already giving us those basic basic elements. So this was totally theoretical article, and there is a good reason why, because if you think about the actual implementation, a lot of like the gate level operations that are done in order just to make multiplication or addition, at the basis, at the basic level, it's a lot of gates. Just as in a classical computer, when you multiply A by B, there are a lot of operation hidden there. So using the Classiq platform, which gives a high-level programming differently from other languages, which are still like assembly, as Eric mentioned, make it impractical to implement such operations like arithmetic. It's telling us that we can maybe actually take this theoretical article and implement it. And 2 weeks after it was published, I took the Classiq Qmod language and I wrote the developments, and I was able to create a big circuit, and I will show you how it was done inside the Mathematica notebook. Okay, so now first time that we see how like implying of how integration with Wolfram can be powerful. We still have more work to do in terms of integration, and of course we need some bigger quantum computers that we can actually run the circuits, but we can create big circuits easily with this combination of Wolfram and Classiq. So for example, let's say that I classically analyze with Wolfram Mathematica Brownian motion modeling. There is like a built-in function of the winner process, which is Brownian motion, and I can look at the goings ups and downs of some asset, or the exponent of it, which is implying that an asset will go down if it's supposed to go down, and might very low. And of course that this is random, and we can run again and look at different occurrences of this behavior. So, and of course we can do some more smarter things inside Wolfram Mathematica, but now let's say that the user would like to investigate the Brownian motion with the computer. So we can import Classiq, install the package, import Classiq, and let's see how can we implement this article using Classiq. So we saw this one, and we say we want to implement quantumly, to make a quantum multiplication of these formulas and quantum summation. By the way, quantum multiplication and summation means that in one operation, for addition, for example, if I have some quantum register A and B, which is in a superposition of many values, So for each of the cases, in each of the worlds that the variable value exists in, I have to do the addition. So this is the actual operation for addition. But in Classiq, it will look almost trivial. It is not in another languages, but as you can see, let's take, let's start with this multiplication and addition. So with Classiq, you do it with just one line. So this multiplication is actually a big quantum circuit, and this entire summation and multiplication, it's a big quantum circuit, and I will show it to you. But it's
now, like, Ron, like,
implemented-
let's provide, like, some context for our audience. Like, you mentioned, Qmod, which is, the programming language that you guys have been developing, like, specifically on quantum. So, elaborate a bit more on that. Like, what is it? Like, when you talk about Qmod, like, what we are talking about, like, and how users should think about that.
Yes. So maybe it's a great question. It will make order of how the language actually looks like. If you start with, let's take the entry point, like where everything starts. So the actual variables, as you see, I told you before that we have QNum. So there is some variable, its name is T, the type is QNum. So behind the scenes, I will show you how the circuit looks like. So behind the scenes, you can see here that T is a quantum variable. In this case, I chose just one qubit, but it could be more, but it represents some variable. And once I have a pointer to this variable, so I can start and make some operation based on this variable. For example, I can do Hadamard transform, which taking T, which starts from a zero state, no superposition, no quantum at all. And once I apply H, I can be in a superposition. And so this is like the most basic thing. More complicated variables are now taking these variables, which are in superposition, and creating even bigger superpositions. And enlarging it more and more. And how it is done in operations that are taking quantum variables. Here are my variables that I need for this summation multiplication, taking the variables and making the multiplication on them, and addition. And let's see how it looks like. So if I zoom in and I look inside, so I see that using the platform, I can take specific variables and make multiplication on them and make subtraction, etc., etc. And then what I actually get is that if I start with some superposition of values of some variables, so I can create new variables with arithmetic operations based on the other one.
Now let's scroll down. Let's look at the final result and because some of our audience, they ask a few questions. Let's look at the final result, and then based on that, I'm gonna ask you some questions. Okay, so here you're adding the constraints.
Yes. So what I would like to mention about, I talked about the language and I show you how you can take a theoretical idea and put it into code. Now, another thing that the compiler is doing is solving optimization problem. Its target is to choose the most optimized implementation for what we wanted. Behind adder, you can implement adder in different ways, but some ways are better in some manners and some are better in other manners. So for example, if I want to compile for Atom computer, I will compile it, I will get some result. And when I will compile it for Ions computer, I will get another result. So like two different implementations.
Got it.
This very big circuit with 130, I don't know how much qubits. So you can see in the data here that I get different results for different types of computer. I could not execute this example because there are too many qubits
Yes.
and the hardware is too noisy and the simulators are too small. But it's just showing you how easy it is with the language to create big circuits. And then the next example, I will show execution.
Okay, so like, there are like, a few questions from our audience, but before jumping to that, like, we have another guest from Classiq joining us, Shai Lev, who is VP of Strategic Partnership at Classiq. Hi, Shai, welcome to our live stream.
Hi, Mads, and thank you for hosting us for this really exciting session.
Sure thing. Like, one of the interesting questions that I guess, like, again, you help me with that is, our users, they just jump ahead and they ask about, like, what's the joint vision of Classiq and Quantum for future of, like, quantum computing. So if you would like to elaborate more on that and the vision that we have in our partnership.
Yeah, so I think that, the vision that we all see in front of our eyes is basically creating the new standard for quantum computing software. And by combining the capabilities of what you guys bring from Wolfram, together with the deep expertise that we have in quantum software, I think that this is something which is really achievable. It took, at the end of the day, creating a quantum computing software is something very wide and very heavy. And if we take a comparison from the classical world, you can't really see any one company doing all of that by itself. I think that joining forces for us, providing this really basic, I would say even operating system for quantum software, together with your expertise and together with your knowledge, that's something which is really, really unique.
Thank you for your input. And this is an invitation for Classiq and Wolfram users in academia, industry, and government. Like, we would love to hear from you guys, like, the real world challenges that you have on applications, on bleeding edge of, like, science and technology. And we would love to help. Like, both companies, they have very unique expertise. And like, and I'm sure, like, it's going to open up, like, lots of new possibilities in the world of quantum. Now, there is another technical questions. I'm going to ask it, like, to Eric. So I appreciate if you opine on that. Like, our users, like, they just jump to very technical question. One of our users, they ask about, like, the future of, quantum classical hybrid approaches. Especially they ask, like, how, like, we think about, the future of high performing computing and HPC facilities.
Yeah, no, that's a great question, right? I go to a lot of these trade shows and events at supercomputing and whatnot, and the vision that the industry has, and not just Classiq on kind of where quantum computing will be at the end of the day, is part of the HPC stack, right? It's going to be part of all these high performance computing systems in the same way that in those systems you have CPUs and you have GPUs and you have TPUs, tensor processing units. You'll also have at the end of the day a QPU. And the same way you send the right kind of data to be processed on the right processor, that's the least intensive for that data to be processed by, you do the same for quantum, right? You wouldn't send all of your graphics to be handled by your CPU. It's less intensive to run it on the GPU, so we send it to that. In the same way, there's going to be types of problems that are much less resource intensive to run on the QPU, and we'll use it for that. And it's going to be this holistic approach at the end of the day, kind of all of these processing units working in chorus and in harmony.
Excellent. And this is like, one of the core areas that, like, both, Classiq and Wolfram, we are actively engaged with our national labs here in US and, other places, because as Eric mentioned, one of the key questions is when you are bringing quantum value into these computations, where it can help the best. And this is basically, like, one of uncharted territories that, like, that I think, like, it is an invitation for many researchers and of course people from the industry that there are very interesting promises from quantum computing. That, the term that we usually use is quantum advantage, but you should keep that in mind that, like, it's a completely non-trivial question to say how quantum value emerges out of your computation. And it needs, like, as Shai mentioned, like, that's why we need to join forces, because these questions are difficult, but both companies, we are actively working on that, and we believe we have some innovative ideas to tackle that. So now I'm gonna go back again, to Ron. And Ron, I know you had some more interesting specific examples on chemistry applications. And by the way, for our audience, we know that we are choosing very simple, cases. It's mostly just to show you, what's possible, and see it as an invitation for you guys to explore more and, help us with innovation.
Great.
Go ahead, Ron.
And
Yes, we can see your screen.
Great, thank you, Matt. And someone asked about the hybrid execution, so it was a great question just before this example, because here we demonstrate the variational quantum eigensolver VQE, which is actually a hybrid algorithm, and how it's done, and how do we leverage the advantages of Wolfram and Classiq in this notebook. So generally speaking, one of the interesting problems which are very important for chemistry applications is finding the minimal energy location for atoms in a molecule, and it's helped them to develop molecules and important materials like fertilizers, for example, in a way which is more efficient, in a way that is less computation intensive. And the VQ is an example. Here, it's just an H2 molecule, a small example, and it shows how can we use Wolfram and Classiq for that. So I will just show what I would like. I will begin with what I would like to show. So in order to solve using Classiq Qmod, the location with the minimal energy of a specific molecule, we use the VQE algorithm. And the VQE algorithm is taking a molecules and running on different combinations and locations, and it will give the minimal energy. Using Classiq, you can define the molecule in a way that is relatively simple. You just have to mention what is the type of the atoms that you are interested, and the location here, which is a variable, because I would like to change it every time and find the best location. And then everything behind the Miltonian construction, all the ugly words that you need for VQE is done using the compiler. And we run a hybrid algorithm, execution of it, using the scene main. It will look a bit more beautiful in the future. It will have just small integration problems with Wolfram, but you can see here we have 4 lines. Please run a VQE algorithm, this quantum circuit, and convert the molecule result accordingly, and give me the actual solution for the molecule. So now, once we finish to run the algorithm, I ran it before the live stream. So we can see that in different location of the hydrogen atom, there are different energies, and we are looking for the location which the energy is minimal. And we would like to use the Wolfram notebook in order to compare between the results that we got from the VQE quantum algorithm and the actual classical result from Wolfram notebook. So let's
Ron, if you scroll up, into that graph, let me just comment on one thing, the dashed line that, that our audience, especially those coming from academia, that's the simplest potential energy surface that you guys may have seen in your physics or chemistry textbook. And what we call as a molecule, in this case, hydrogen molecule, it lives at the bottom of that well. So basically, that's the most stable, place, and the molecule leaves that there. And this potential energy, the simplest one, it has also another term, they call it most potential energy in the literature. And you see, this is obtained using a fully quantum approach. It's completely, by quantum, I mean quantum computing approach, not the conventional approach that we have in computational chemistry.
Yeah, great. Thanks, Matt. And I will show you right now what is the solution from the classical world, which of course I will do with Wolfram. So with Wolfram, all I have to do is to define the molecule, and I'm asking Wolfram to give me the actual distance between the atoms, which is with minimal energy. So Wolfram is telling me the classical solution, what we tell you is the optimal solution is 0.54 angstrom. And this is the solution. And now we would like to check if the solution of VQE using Classiq was the same. Of course, that it depends on the steps that I chose. If it was dense enough, so it will affect the resolution. But we would like to see if this number is close enough to the actual VQE solution with Classiq. And we can visualize, again, using Wolfram, we can visualize the molecules and see that for different distances, there are different energies. So we see here that the energy is minimal, 0.8. So this is telling me using VQE that the location, the distance between the atoms at 0.8 is really very close to the classical solution, which tells me that this is true. And we can see it also here in this nice graph. So it was, of course, a very simple example of just two hydrogens molecules. But if you go to the world of fertilizers, for example, like very big molecules, there are very important applications for finding such optimal solution. Those are solutions that are still not known to the classical algorithms because the running times is too big, and we have hopes that this will bring developments of material, of medicines, anything is in the chemistry world.
Excellent. And by the way, for your audience, yes, we will share these notebooks, for sure, you can use them and you can replicate the results. There are a couple of other interesting questions, some of them, man, very technical questions. Our users, they usually love to ask technical questions. So, talking about maybe I'm gonna ask one of these questions from Shai. So one of our users, they are asking they are interested to collaborate with Wolfram plus Classiq team, how they should contact us, well, that's basically the detailed question that they are asking.
Great. So I saw the question, and definitely reach out to us either via Quantum at Wolfram or via ron@classiq.io. And I think that for us, we understand that we're just at the beginning of this journey, and definitely one of the things that we're looking here together, both Wolfram and us, is to know the users better, to know what we can do together in a wider scope of work, because at the end of the day, it will take a village. It won't be done only by Wolfram and by Classiq together. We need to see what is out there, what is interesting people, and that's definitely something that we would love to explore together. So feel free to reach out. And Mads, maybe one point about the HPC center and the integration. I think that we talked nicely about the technical aspect. I think that one of the interesting things to see is that when these kind of centers, high performance computing centers, start looking at their quantum strategy, and they actually even buy a QPU to be an enhancer, etc., that's only their start. I mean, the work that needs to be done on the integration and on the software level and on the application level is very important and very heavy lifting. And I think that that's one of the places that together, as you mentioned, with national labs here in the United States or elsewhere, we can definitely bring the contribution to take that steps forward. So this is, I think, as you mentioned, one of the most exciting aspects of this collaboration.
Definitely, one more time, we are, in a live stream, we share our email contact, Classiq PR at, I just share it with my team, they're gonna put it on the live stream, so the users, they can directly reach out to Classiq team, they can directly reach out to Wolfram team. And yes, like, this is the area that, like, in near future, we will see, like, lots of interesting applications. And, like, one thing that, like, we are really, at least from Wolfram side, like, have been enjoying, like, our collaboration and partnership with Classiq is both of us, we care a lot about real world application. So we are very good, 35 years of, like, Wolfram, engagement with academia, like, we know that we are very good in, like, doing original research the way that it is done in academia, but on quantum, in addition to that, we would love to see real world application. And this is the part that, like, the partnership and joining forces with a, like, a company such as Classiq brings lots of value, because they are the one who are, like, focused specifically on, like, the best quantum algorithms and the best for like, specific applications. Now, again, talking about, like, high performance, like, integration, there is another, detailed question. Eric, Ron, whoever wants to opine on that. Our users are asking, in terms of, software design, like, model view controller, like, where do you see, like, the integration or the true value of quantum? Like, would it be in, like, modeling development? Would it be, like, somewhere else? Like, that's that they want to hear more details on that.
Eric,
Yeah,
would you like?
I go for it, Ron, or do you want me to take that one?
Yeah, go ahead.
Yeah. I mean, I'll talk a little bit about our language and kind of how we structure it and how that can affect things and play around with things, right? So, the Qmod language that you were seeing, Ron demonstrating, it's a declarative programming language, higher level abstracted above kind of assembly, right? So it's much friendlier to code in and kind of lets you abstract out to any of the lower level coding languages out there and available. Because every hardware manufacturer has their own low level coding language, right? IBM has OpenChasm with their whole Qiskit thing, and Microsoft has Q Sharp, and Google has Circ. So programming at a higher level helps you integrate and work with any of these kind of lower levels. So if we're looking at kind of the quantum stack, you would say, right, Classiq would be a higher level abstracted language that then compiles down to any of these lower level languages that then get interpreted by the quantum processor, and then that processor, when it hits the software hardware boundary, it needs to make sure that are all the operations actually native to the hardware it's running on? How do you interpret these kind of machine code operations into the system? Let's see. I'm trying to make sure that I hit the question right, or was it slightly different than what we were getting at here?
No, that was very helpful. Like, Ron, like, would you like to add more on that?
Can you elaborate the question? I try to understand.
So basically, like, think about like this, like, so we have, like, a great classical algorithm, okay, and we can run it in one of, like, these HPC facilities. And now we are thinking about, like, quantum. So where in this workflow, like, it has many steps. It has, like, integration with the hardware. It has, like, code design. It's just, like, analyzing the data at the very end, like, the data that, like, you get after, like, the machine does all the grinding. So when you think about, like, quantum, like that, the case of, the finance case, like, that you just showed at the beginning, why somebody should say, okay, why I should care about quantum? Where in this workflow is going to bring a value, because I have a good classical algorithm and I can run it on my HPC facilities.
Yeah, sure. So this field of quantum advantage is very interesting. The most interest is in the area of the computer scientists that explore what is the actual advantage. So there's like families of algorithms, and each one of them is given different advantage. So first, of course, is the most non-proven advantage, no proven yet for quantum machine learning and the variational algorithms and things like that. People trying, there's no proven advantage. People do find them useful and try to prove it and bring it, but no proven yet. And then at the next level, you have the quadratic advantage. So it means that if something's with a classical computer takes you x, so with a quantum computer, it will take like the square root of x. So this is a quadratic advantage, like the Grover algorithm, which is doing searching, like Bitcoin mining and things like that. Also, the financial algorithms, like the one I mentioned before, option pricing and things like that. So we see a quadratic advantage. Quadratic might be maybe not good enough, but of course it's very important when you are in financial market, and the one which is fastest is the winner and things like that. And the best family of advantage is the exponential advantage, which is splitted into three main algorithms. One is physics and chemistry, which is like the most maybe important thing, discover medicines and biology and everything. So it's very important for physicists. Then is the cybersecurity, the Shor algorithm, which is can crack any RSA encryption, and we see the entire world is changing the encryption because of the coming quantum computer. And then the last family maybe that I have in my head, at least for exponential advantage, is HHL. And HHL is inverting a matrix in a logarithmic complexity rather than polynomial. So it gives you exponential advantage over classical methods. So in any application where you have to invert a matrix, and there are many of them, let's say a differential equation solver for, there are applications we are working with our clients, it gives also exponential advantage. Now, maybe to complete the answer to the question, if you was asking where is the software coming in this pipeline, so in my imagination, maybe I will share my screen, it will maybe help to give better view. So just from looking at the Classiq platform, where there is a model which is defining in a high-level language something, and you can choose it from a big libraries of many examples, and then you can synthesize to compile to a specific backend, visualize it, and then execute it into some environment, in any environment. Maybe it will be HPC, maybe not. Maybe it will be hybrid and maybe not. So there's like, we can imagine that we can connect to many different hardwares. So this is currently how it looks like. And then once it's inside an HPC, so I imagine a cooperation of this software is like, we call it on-prem, is sitting inside the HPC and not online, able to create the circuits, to create the logical circuits. Also able, maybe we don't do it today, we have just POCs to create also the error correction software stack, and to manage the entire operation based on those examples.
Now, like, there is another interesting question by another users, like, which is a good continuation of what you just explained, Ron. So why you guys decided to go toward high-level programming rather than, like, very low level for quantum? Like, what's the benefit of going to the high level?
Yes, so maybe the best explanation, I just today, this morning, I answered many people about quantum adder, which I mentioned before. This is just one example, but I think it's emphasized the best why do we need it. Let's take a look on answers. So people was very confused of managing and following exactly the qubits when they, just a moment. I'm searching, sorry.
You answered too many questions.
Yeah.
I'm surprised that, like, Ron is bravely sharing, like, his whole screen. Like, it's a scary thing to do so, but he's so brave.
Yeah, so you can see people were very struggling to implement, as Eric said grossly impractical to make an adder at the very
Mm-hmm,
level.
mm-hmm, mm-hmm.
So, and following the qubits, what is the fraction? What are the qubits that represent the fraction, or what represent the sign? So with Classiq, it's just as you do with Python or any other high level. Also, using the compiler, you don't have to manage and be aware of your specific hardware. You just write what you want to do rather than how you want to do. And then once you compile it, you just choose which hardware you want to run on.
Mm-hmm,
And
mm-hmm.
so this, I hope this is answering the question of why
Yes.
what is the high level.
Yes.
And I think that, Mads, it also connects to the point that you mentioned before about both companies having such a great collaboration, not only because of, you know, we like each other and the nice smiles, but also because we have a similar approach of being very practical.
Mm-hmm.
And when you want to be very practical, I think that the high level approach is, you know, is the one that you basically need. If you're looking into the future and you're seeing, okay, we want to get more complex, more sophistication, I see that as a main anchor, you know, in the vision.
Absolutely. I agree with that. I mean, I was even thinking about what Ron was saying earlier about kind of these proven out quantum algorithms that have this exponential speed up, like HHL, things like that. There's so many applications for these things, but when you think about the practical use of these applications, right? HHL can solve linear systems of equations. And if you look at what that can be, that's a lot of physics simulations like computational fluid dynamics, you know, how water flows, how fire flows, turbulence. And this plays into really huge applications that a number of industries are trying to do, like digital twin simulations, right? Trying to build these whole real world simulation ecosystems that can mimic the real world, and you can kind of prototype your environment in real life. And what's stopping that from becoming more of a reality is the computational intensity of building that out. And quantum computing is going to be a piece of the puzzle that helps lower the intensity, you know, the computational requirements to
Mm-hmm.
enable.
Definitely. So I'm gonna bravely share my screen, like, related to that question of like, high level, like, programming language. This is also like, as many people know, like, that's the core idea behind like, Wolfram language and mathematical environment. Like, what we try to do is to help users to have an experience that is as close as they can to what we call as computational thinking. For example, like, look at like, let's go through like, this line of codes, like, here a user saying, like, even like, when you are not even an expert, you would say like, I'm creating a quantum state. The amplitudes are random real numbers. I'm creating 8 of them, and then I'm gonna normalize that state. And this is basically the list of amplitudes on that state. And the next level, I'm gonna say, now create a quantum circuit operator and, connect with Classiq. And then from Classiq, like, the bound, like, this is the bound that I'm gonna set for like, the target, probability. And this is basically like, the philosophy that we have, like, in both Classiq, you remember, like, in our audience, like the example that Ron showed you, like, you could open up like, a cell in any other programming language, and you can go into all the details of like, how to get it done at that level, or you can do it at this level, and basically not thinking about like how behind the scene, things are done. And this is basically the strategy of like, both companies. Like, we are very good creating the products at a high level that is very useful for the users, the end user from the industry. Basically, like, a common thing that we usually, tell to many people is quantum applications should not be for a user with a PhD in quantum. Okay, this is not the right strategy. When we are training the future, quantum workforces, we shouldn't think about, oh, all of them, they should have a like, PhD or master in quantum in order to be able to use like, these interesting functionalities. Like even somebody who is major in humanities and they want to do an optimization, but they know that like, okay, I would love to use like, quantum advantage for that optimization. They should be able to run those algorithms. And this is, in a sense, the philosophy behind this high-level programming that we follow in Wolfram research and also Classiq. So we are almost like, on time, like, the last few minutes, our great guests, like, Shai, Eric, Ron, any final words that you would like to share with our users?
I would be happy to say that, like, being practical just before we finish, if our audience feels that they are now very passionate, they want to try it by themselves, just open a Wolfram Mathematica notebook, and you can take from the big library. We have also the Git library. Just write in Google Classiq library, and there are like hundreds of examples from applications or algorithms, and you can copy paste the code into Wolfram Mathematica. Try to do the own by yourself. The same example is also in our GUI the ID, and we also have the user guide, like docs at .classiq.io. You can take the example, you can download them, paste them, and just try to copy paste and do it by yourself. You will see very easy.
And if any question, do not hesitate to ask. You see Ron himself, like, he is very active, asking, responding to any detailed question. And the same, like, with Wolfram, like, please, from the documentation, copy and paste the code and ask questions. Like, both companies are very committed to help our users with any detailed questions that they may have.
And talk to us. As we said before, you have the contact details of both companies. We're looking to expand these efforts beyond just work between Classiq and Wolfram, and we'll be happy to collaborate around numerous interest areas. So please feel free to talk to us, and we can get some exciting things on the way.
Ooh, I'm excited to see what the quantum wish list comes out of this stream looks like.
Yes. Thank you, everyone. I'm gonna hand back to Yi. Any final word, like, Yi, from your side?
Thanks everyone for joining us. If you have any additional questions, shoot us an email.
Excellent. And Ron, like, any final word on this? You share your screen, like, you wanted
I'm
to
sorry. I thought that just before we finish, maybe the best thing I would allow myself to do now, and I welcome you to join, is I would open a channel in the Classiq Slack, Wolfram Classiq community. I welcome you to share whatever you like, to ask questions, to put your own examples inside. We will be more than happy.
Excellent. Do you mind, like, to share that link so we can also, like, pass, put it in the live stream, the link on that Slack channel?
Yes. So
that doesn't get more practical than this, huh?
We are doing everything live. If you put it in the Zoom chat, like, I'm gonna, share with our team. They can take it and put it on.
Yeah.
Yes. Okay. Excellent. So we are gonna put it. Okay. So we are gonna put it now on the YouTube channel. Excellent. So please join and ask your questions.
Yeah. Thanks everyone. We will see you on the Slack channel.